The second part of 3.2 has to deal with something called the mean value theorem, which is going to come in real important in proving the fundamental theorem of calculus. And so it has the same conditions really or the first two conditions of Rolle's theorem, in that the function has to be continuous on the closed interval and then differentiable on the open interval. It doesn't have the third condition where the endpoints have to be equal. However, the conclusion's a bit different. There exists a c in the open interval AB such that the derivative at that particular point is equal to the secant line between the 2 points. And this is kind of nice, especially when we prove the fundamental theorem of calculus. So if we want to find the slope is just going to be the difference in the y coordinates over the difference in the x coordinates, and then we're going to use our point x1 y1 as a comma f of a in the point slope formula. So what it's going to be is y minus f of a, that's y minus y1, y minus f of a is equal to m times x minus x1. M is going to be the slope of the secant, and then we'll leave it as x minus a. And then what we'll do is, so the last thing we do is we go ahead and add f of a to both sides. And this is the equation of the secant line connecting the two endpoints. And then you see the yellow line there. We can use our imagination a little bit, but that's the tangent line that has the same slope. So this is going to show existence. It's not going to quite prove it, but its existence, and we can often use this to find that particular point that has the same slope as the secant line. So instead of setting our derivative equal to 0, we might set it equal to the secant line slope. Alright, so what we're going to do is we're going to put g of x to be equal to f of x minus that line. So f of x minus the line, the secant line, f of b minus f of a all over b minus a, times x minus a minus f of a. Now g is just a sum of differentiable functions, f of x, and the only thing that's really a function here is just the x. The rest of the stuff there is constant. That and the f of x. Those are the only things that might change. Everything else is a constant. So it's going to be continuous on the closed interval AB, and it's also going to be differentiable on the open interval AB. And what we're going to do is we're going to check the endpoints. If the endpoints outputs are the same, then we're going to be able to apply Rolle's theorem. So if we plug in g of a, or a into this, you see that the a minus a here is going to make this whole big term 0, and then you're going to have f of a minus f of a, which is just 0. Then if we plug b in, what's going to happen here is the b minus a's are going to cancel. When I distribute this negative sign through, you'll have an f of b minus f of b, so those are gone, and then the minus will make f of a, and then we have a minus f of a over here. So everything cancels out, and we're left with just 0 again. And I'll mention again, g is continuous on the closed interval AB, and differentiable on the open interval AB. And we saw that the endpoints were equal, so the Rolle's theorem applies. So what that means, there exists a c in AB such that the g prime of c is equal to 0. Okay. Now remember we said at the beginning that we could take the derivative of this g function here. So we're going to get the derivative of f as f prime. The derivative of f of a is just going to be 0 because it's a constant. And then the x minus a, the derivative of the a is going to be 0, the derivative of the x is going to be 1, so we'll just have f of b minus f of a all over b minus a times 1. f of b minus f of a all over b minus a, and that's equal to 0. So if we add f of b minus f of a to both sides, we get exactly what we want. We have f prime of c is equal to f of b minus f of a all over b minus a. Alright, for our first example, we're going to see if the mean value theorem applies. 2x cubed is just a polynomial, so it's going to be continuous on the real numbers and differentiable on the real numbers. So the first two conditions of the mean value theorem are met, so mean value theorem will apply here. We need to find the slope of the secant line connecting the endpoints, so we need to find f of 6 minus f of 0 all over 6 minus 0. That's 72. And then we're going to take our derivative, and we're going to set it equal to the slope of our secant line. So instead of setting a derivative equal to 0, that would be locating places where we have a horizontal tangent. Here we're going to be looking for having a tangent line that has a slope of 72. So if we solve this, we'd divide both sides by 6, and we'd get 18. If we take the square root of that, we'll get plus or minus 3 root 2. And the only one we'll consider is 3 square root of 2, because the negative 3 root 2 is not in our interval of consideration. Now, in terms of a picture, this would be kind of difficult to see because a line with slope 72 is going to be growing pretty fast. All right, let's take a look at another example here where we have another function here. F of x is equal to x plus 1 all over x. And we're going to look at it on the interval -1 to 1. So the important thing to remember is not to be carried away with just the mechanics doing the problem. You have to actually think, does it meet the conditions? Is f continuous on -1 to 1? And the answer is no, because I can't plug 0 in. It's undefined at 0, so it's discontinuous, or not continuous on -1 to 1. So the mean value theorem doesn't apply. Now let's say we just got carried away and we started doing this, and we would have gotten a slope of 1/4, and if we take the derivative we get -1 over x squared, and we would set the derivative equal to the secant line slope, and if we solve that we would get plus and minus 2i, which is imaginary, and we're trying to keep it real here. So no imaginary numbers, we're not graphing on the imaginary axis, anything like this. So mean value theorem does not apply, and if we still go through and try to use it, we're going to get something that doesn't make sense because we're not graphing anything on the complex plane. So don't get carried away, try to make sure that the assumptions hold true. Alright, let's look at another example here. We're going to look at the square root of 2 minus x on the closed interval -7 to 2. -7 to 2 is part of the domain of this function, so we're okay there. It's continuous on that closed interval. If I take the derivative, I'm going to have a square root of 2 minus x in the denominator, and that's going to be undefined for numbers 2 and larger. So it will be differentiable on the open interval -7 to 2. So we're okay there. So it's going to be continuous on the closed interval -7 to 2, and differentiable on the open interval -7 to 2. And now we need to find the slope of the secant line. So we're going to go ahead and do that. And we're going to get -1/3 as our slope of our secant line. If we take the derivative, now the 1/2 comes down, 2 minus x to the -1/2 using the power rule. We're also going to have to use the chain rule because we have a minus x, so when we take the derivative of the 2 minus x, we're going to have a -1 left over. Okay, and there's our derivative, -1 over 2 times the square root of 2 minus x, and we're going to set it equal to the slope of the secant line, which is -1/3. We're going to go ahead and cross multiply. 3 times the 1 will give us a 3. We have negative on both sides, the negatives will cancel out. So 3 is going to be equal to 2 times square root of 2 minus x. To undo a square, we're going to square both sides. 9 equals 4 times the quantity 2 minus x. We're going to divide both sides by 4, which will give us 9 over 4. Alright, so we have 9 over 4, which is the same thing as 2 and a fourth. And then we're going to subtract 2, so we'll have a remainder of 1/4 is equal to negative x. And then we will multiply by negative 1, and at this particular point, at negative 1/4, is where we're going to have the slope of this, the tangent line is going to be equal to negative 1/4. And if we look at the next slide here, we have a picture here. So the red graph is the square root function. You see the blue line is a secant line connecting the point 2, 0 with negative 7 and 9. And then you see the green line there, that's the tangent line at negative 1/4. It might be a little bit difficult to see, but you can definitely tell that the green and the blue line have the same slope. So this would be an illustration of the mean value theorem. And the last example we'll look at is sine of x on the closed interval 0 to pi. The sine is continuous on the closed interval 0 to pi, and it's differentiable on the open interval 0 to pi. It's actually continuous and differentiable on the whole real number line, so it certainly meets the conditions of mean value theorem. So we'll find the slope of the secant line connecting the endpoints. Sine of pi and sine of 0 are both 0, so we have 0 in the numerator and pi in the denominator, so we got a slope of 0. Take the derivative of sine, we get cosine, set it equal to the slope of the secant line, and cosine of x is equal to 0 when x is equal to pi over 2, 3 pi over 2, 5 pi over 2, and then also the negative versions. But since we're looking at only the interval 0 to pi, the only one that fits is pi over 2. So if we draw ourselves a picture of the sine, so sine starts at 0, and we can go ahead and use our imagination that these two lines are in fact parallel. Here we have the secant line connecting 0 to pi, and then here we have the tangent. We have the tangent line right there that we said we had a horizontal tangent of pi over 2. So, mean value theorem and Rolle's theorem have similar assumptions or hypotheses that need to be met. Continuous on the closed interval, open on the and differentiable on the open interval. If you have those two conditions met, you can use the mean value theorem. And if you're going to use Rolle's theorem, you have one more condition, and that's that the output of the endpoints have to be equal. So your homework is going to be having you use Rolle's theorem and mean value theorem. Where does it apply? Where does it not apply? And where it's not going to apply is if you have some sort of discontinuity or somewhere it's not differentiable, maybe the endpoints aren't equal, that kind of stuff. So, try to get through most of that homework during a spring break. It won't be too difficult.